Hello and welcome to the third week of the course. Last week we looked at sedimentation and filtration, which are ways to remove suspended particles from water. This week we focus in on disinfection processes that result in high levels of removal or inactivation of the different classes of pathogens. We'll start by looking at heat. Heat, in fact, kills through different mechanisms. Heat impacts enzymes and causes them to denature and become non-functional. It can affect the proteins that make up cells and cause them to unfold and change their shape. And also within a cell, it can increase the pressure, which damages cells. We'll look at two broad classes of heat treatment, boiling and pasteurization. To understand how heat disinfection works, we have to first think a little bit about temperature and pressure, and recognize that pressure affects the boiling point. If the pressure is higher, then the boiling point can be higher. And in fact, this is how an autoclave works, with steam sterilization at high pressure, about 1 bar above atmospheric pressure, and that allows water to reach 121 degrees Celsius. And if it's kept there for 15 minutes, under steam, it's a very effective sterilization technique. Conversely, if the air pressure is lower, the boiling temperature is also lower, and we'll discuss the implications that that can have on boiling. With disinfection processes, both the amount of disinfectant present and the time that the pathogens are exposed have an impact on removal efficiency. For heat disinfection, then, we can think of both the temperature and the time of exposure and recognize that at higher temperatures, a shorter time of treatment is required to achieve an equivalent amount of pathogen reduction. The thermal death kinetics of heat disinfection are assumed to follow first order or exponential decay, which means that a fixed amount of time is required to achieve one log reduction value. This is called a D value, typically set at 121 Celsius. And if a D value for one pathogen was 10 minutes, then after 10 minutes, 90% of that pathogen would have been inactivated. After 20 minutes, it would be 99%, and so on and so on. The food canning industry is very concerned about thermal death kinetics because food are pasteurized before canning, and canned food can be on shelves for a long time, months, even years, before being consumed. So the guidelines are very strict for ensuring high levels of disinfection, with a 12D reduction of Clostridium botulinum spores being a typical industry standard. Drinking water treatment is normally less strict. Drinking water doesn't sit on shelves for years before being consumed, and typically 7 log reduction is considered as complete disinfection for practical purposes. Boiling is the oldest method of household water treatment, and today it's practiced by an estimated 600 million people around the world. It's particularly common in East Asia and in Uzbekistan, Mongolia, Vietnam, and Indonesia. More than 90% of the population report boiling their water regularly before drinking it. Boiling is effective against all classes of pathogens, viruses, bacteria, and protozoa, and it's not affected by turbidity in water, unlike some other disinfection processes. However, after water is boiled, it must be cooled before drinking, and it's often transferred to a secondary container where it's quite prone to recontamination. Finally, boiling removes all dissolved gases from water, which gives it changes the taste of the water and can give it a flat taste. And if the water is hard, calcium and magnesium can precipitate out, forming small white particles, which can cause aesthetic problems. In recent years, a number of studies have examined the effectiveness of boiling as applied in different countries. These studies have found significant reductions in indicator bacteria, usually thermotolerant coliforms, but have also documented substantial recontamination of water, with roughly half to 60, maybe 70% of samples having no detectable indicator bacteria. However, the level of contamination tends to be small, with roughly 75% of samples falling into the low-risk class of having less than 10 colony-forming units per 100 mils. Also, the log reduction values of 1 to 2 may also reflect relatively good quality of the pre-treated water. If the pre-treated water has low to medium levels of contamination, it's very difficult to demonstrate higher levels of removal. In many low and middle income countries, when boiling is practiced, biomass, either wood or some crop residues or other materials, are used as the fuel, and this can have substantial negative impacts. First, there can be health impacts. If biomass is burnt inside the house, a lot of soot and smoke is generated, which has serious negative impacts on health. It's a risk factor for lower respiratory infections, which are a major cause of child mortality. Biomass burning also has negative environmental impacts, where deforestation can be exacerbated by widespread use of biomass, as well as the release of CO2 and smoke into the immediate environment. Finally, burning of biomass can be very costly in terms of both the fuel itself and the time that's needed. Two of those studies from the previous page, done in India and Vietnam, also examined the cost of boiling and found that the fuel cost alone was around 0.5 to 1.5% of monthly income, but that substantial amounts of time were needed, either for collecting fuel if it's not bought, or for taking extra time to treat the water in the home, and that these have significant economic impacts, equivalent to possibly 2 to 5% of monthly income. While boiling is highly effective against all classes of pathogens, it's not actually necessary to reach 100 degrees to get good log reduction values. The mechanisms by which heat operates, enzyme denaturing, protein damage, and increasing pressure within cells, are having impacts at much lower temperatures. In fact, it's possible to cook an egg at 72 degrees. This is high enough to damage the proteins, causing the whites and the yolk to become opaque. Similarly, milk pasteurization is done at 72 degrees for only 15 seconds. At a lower temperature of 63 degrees Celsius, 30 minutes are required for pasteurization, and both of these achieve roughly 7 log reduction of common pathogens. Recall also that the heat-up time and the cool-down time contribute to pathogen reduction, so it's really not necessary to bring the water to a full boil to get effective treatment. The problem, of course, that it's difficult to know when you've reached an effective treatment temperature like 70 degrees for pasteurization. One tool that can help is called a WAPI, or a water pasteurization indicator. It's a small tube that has a little glob of wax which melts at 70 or some specified temperature. Perhaps because of the difficulties in determining when an appropriate pasteurization temperature has been reached, there's been relatively little experience with pasteurization as a household water treatment system. One example, though, comes from Bangladesh, which was developed by Professor Fakhrul Islam at Rajshahi University. And this is called the Chulli system, and it takes advantage of readily available waste heat that comes from inefficient cook stoves, homemade clay stoves which reach a temperature of about 600 degrees, but more than 80% of that heat is wasted. So Professor Islam developed a metal coil made out of aluminum, which acts as a heat exchanger. And when this coil is built into a cook stove, water can be passed through the coil during cooking, and water heated up to the pasteurization temperature before it comes out the other side. Here's what it looks like in practice. That coil is built into a clay cook stove and then attached to a reservoir for raw water that then feeds the water through a tube into the coil during cooking, and it comes out through a tap into a storage container. Now, the nice thing about this system is it doesn't take additional fuel because it takes advantage of heat that's already being used for cooking. However, an evaluation made in 2007 found that while it was microbiologically effective, with a medium of 5 LRV of E. coli, only about 20% of people who received the Chulli systems were actually using them. So compliance was a definite problem. Heat disinfection is widely effective against all classes of pathogens, with 6 to even more than 9 log reduction values possible. Some of the pathogens which are particularly resistant to other treatment processes, filtration or chlorine, for example, are very vulnerable to heat. So we see that Cryptosporidium cysts can be inactivated after just 1 minute at 72 degrees. And viruses are easily killed, some of them even at 60 degrees. Many studies have been done on bacteria, many from the food industry. And again, these are vulnerable. There are some special examples of things like anthrax spores, which can actually survive boiling for several minutes. But the pathogens of concern in drinking water tend to be vulnerable to heat treatment. For a more detailed review of heat sensitivity of different pathogens, here are 2 articles which are freely available on the internet. The top one also describes the Chulli water treatment system in more detail. Now recall that pressure affects the boiling temperature, and at lower pressures, water boils at a lower temperature. Well, on this Earth, we have elevations ranging from negative 427 meters to 8,848 meters on top of Mount Everest. And what impact does that have on boiling temperatures? Well, of course, at mean sea level, the boiling temperature is 100 degrees. It's the same in Dhaka at 4 meters above sea level. It's pretty much the same in Dubendorf, home of Eilvag in Switzerland. And if we look at some of the high cities in the world, Addis Ababa, La Paz, Aspen, we see boiling temperatures of around 90 degrees. If we would go all the way to the top of Mount Everest and boil some water, it would be at 72 degrees, which we have seen is an effective pasteurization temperature. At La Rinconada in Peru, the highest continuously inhabited place on Earth, water boils at 83 degrees. So while it's true that water boils at lower temperatures, you're still getting effective pathogen removal at any of these temperatures if the water boils at all. By the way, just for information, altitude also affects the amount of oxygen available, the relative oxygen compared to mean sea level. So in a place like Addis Ababa, there's a lot less oxygen around. And of course, if you're on top of Mount Everest, you're only having about 1/3 as much oxygen as you would at sea level. So then, how long is it necessary to boil water for? Some organizations recommend 10 minutes, 20 minutes, or even longer. And while this may be necessary to really inactivate the most recalcitrant of microbes like anthrax spores, it is not necessary for the pathogens of most concern in drinking water. Leading causes of diarrheal disease, Giardia, Cryptosporidium, enteric bacteria, and viruses are all relatively vulnerable to heat. Pasteurization alone should give adequate protection for drinking water, and anywhere in the world that you can boil water, the water will reach at least 70 degrees and be effectively pasteurized. Remember, too, that pathogens die off during the warming up and boiling off phases as well, so by the time water boils, even a tiny bit, at any altitude, most of the pathogens have already been killed. Now, I don't recommend boiling water on top of Everest, not least because there's hardly any oxygen up there, but for a water treatment practice, it would still count as pasteurization. WHO recommends that water should be brought to a full rolling boil, and while this is actually more heat treatment than is needed, it does give a clear objective signal that the disinfection temperature has been reached. Some considerations then for heat treatment, both boiling and pasteurization then, are that it is highly effective against all classes of pathogens, and that it's not affected by turbidity as some other treatment processes are. However, it does take a long time, especially when cooling time is added or collecting of firewood, and it does change the taste of the water, which some people might not like. It's very simple to operate. No special equipment is needed for boiling. though there is a possibility, a significant one, of recontamination. Finally, boiling is widely accepted, understood, and even promoted all around the world. And maybe one of the most significant challenges is the high energy and time costs required to boil water in the home. So in summary, we've seen that heat kills. It is an effective household water treatment process, effective against all classes of pathogens, whether boiling or pasteurization is used. Boiling is very widespread. It is the most commonly practiced of the HWTS options, but recontamination of boiled water is also very widespread. Pasteurization works well technically, but is much less widely applied.